Welcome y'all to another episode of Shenzhen I, episode 7. And we finished up the creepy doll and the change making machine last time. This time we're going to go take a look at the sandwich maker, because who doesn't like sandwiches? So we know we have a single X bus input, we have a whole bunch of outputs. We have the options of bread, meat, cheese, mustard, and a flag after it's done, and we need to do this depending on what button is pressed. We have a regular that has everything, we have one without cheese, and then we have one with extra mustard. So there will always be bread and meat. Sorry, there will always be bread, meat, and mustard, and a flag. Depends on whether there's extra mustard or not. Okay, so let's start with one. We're going to hold this one kind of close over here so that we have room. Since the meat, cheese, and mustard's kind of a little odd, let's go throw this at it. So we can take advantage of gen pulse first, like the bread and the flag. With that in mind, let's actually move everything kind of a little bit closer up. And this will be our bread output. And we'll try making this one the flag output. And then let's run you through like that. You go there, and you go there. Let's start writing some code. So first we want to just sleep until we get the data. Then we want to save it off to the DAT in case we want to do any math. And we're going to do a quick pulse on v1 for the bread. And we can move 100 to x3 because the gen pulse automatically sleeps. Sleep 1. If we're equal to 2, if we are not, we have a 10 to x3 and sleep 1. So now we do the mustard. 1 to x3. For a 3, we need to do extra mustard. And we do not have enough lines because we need to reset x3 to 0 and then also do 2 more pulses. 1 for the bread and 1 for the flag. So we're going to need another chip. Since we don't need any simple I/O lines, we can grab this one. Then what we want to do here is we want to, instead of outputting that 1, we want to move our DAT to x3. Sleep 1. And see if the DAT is equal to 3. Sleep another 1. Since it's going to do the mustard, and it's always going to do 1 cycle, which is what our first sleep was after sending the signal to it. And then the next one after that will be it's a 3, so extra mustard, then we need to sleep an extra cycle. And then we just have our 2 gen pulses. 1 for the bread, and then the flag, which looks like it is 1, 2, 3. So 3 cycle. D0, 3, 0. So then we just need here. And so we just sleep until x0. And then we move x0 to the accumulator. And then we move the accumulator to x3. We know there's only 3 inputs that it can be. It can either be a meat, a cheese, or mustard. If it's a meat or cheese, we know that there will always be another command following it immediately to reset the output to something else. And it's only the time when it's the mustard do we need to clean up after ourselves. Let's just take that assumption and say if we're equal to 3, we always need to sleep 1. And if we're 3, we need to sleep 2. And then we need to move 0 to x3. Unfortunately, that's some wasted power moving that 0 to x3 every time for the cases where we're 10 or 100. Extra 2 lines of code, but should cut our power usage down a bit. Since we know we will always have a mustard command, we can always assume that we will be the last ones that need to clean up after ourselves. So let's give that a shot. Where it breaks. Oop, a 2. Why did a 2 break? Because we don't know how to spell DAT correctly. Gotta clear a breakpoint. Pretty good. So yeah, our power usage wasn't great, but our production costs and number of lines of code wasn't bad. Like somebody was able to figure out how to get a ROM to work. Really like to, but I just don't see it happening. That was pretty fun. Okay. Sounds like fun. I think I'll pass. All right, let's go check out the Carbine target illuminator. Yeah, does stuff depending on distance. Okay, shouldn't be too bad. Go take a look at the specs for it real quick. So as we can see, depending on the distance, it has a couple different modes, and the laser has variable output, and then it looks like we have some discrete outputs for the flood part of it. Okay, shouldn't be too bad then. All right, and so here's the board. We're supposed to ping something, and depending on the amount of time units that we get a return ping, dictates what mode we operate in. So since this needs to be a variable output, and these both need to actually be discrete outputs, I think we're going to throw one of these at it. And let's start with one of these here. Make that a little bit closer in long runs, in case we need the room. And then we will add or subtract chips as needed. To start with, let's have a start. And we probably need to check our verification to see what we're looking at. Okay, the radar out is also an input. We need to start measuring time from when we get a non-zero value. So we just need to wait for P1 not to be 0. So we're going to do something a little different, and we're going to do that check, and then we're going to just immediately sleep, because we won't be able to do anything with that value regardless until at least a cycle or two down the road. So instead of trying to store it off and then having to check again next cycle that we had stored it off the previous cycle, we can use the way the tests set enable and disable the pluses and minuses in between sleeps. Sleep 1. And if it did, we need to jump back to start. Otherwise, we go into a wait loop, and here we need to wait until radar in is 100. So we just need to test for P0 equals 100. And before we start doing any of our other checks, we need to add one, since it's been one time unit. And if it's not 100, we need to sleep 1 and jump back to wait. And now that we've done that, now we need to actually do something with those values. We go back and look at our spec sheet. So we have 3 states. I think we can get away with just checking for 2 states and then defaulting to the other state that we didn't check for otherwise. So first thing we need to do is check to see if the accumulator is greater than 4. And looking at our input, I just realized that we are missing an output. We're going to have to add a second chip, unfortunately. So as usual, we'll grab a big one so that we have room if we need it, and we will reduce our size if we don't. Since we're going to add a second chip anyways, I want to go ahead and just have it handle all the actual processing stuff. We'll have the first chip responsible for handling the radar pulse and determining how long it is, and then we'll let the second chip then do the processing from then on out. So we can get rid of that. And we can move our value from the accumulator to X3. And then we'll want to reset our accumulator. And we'll probably want to do some cheeky sleeping here, which we'll have to test later. So let's just say we'll sleep 2. Okay, so here we'll want to sleep until we get some data. And then once we do get data, we're going to want to save that off. So let's save that off to the DAT. Now we need to run through our different cases. Test greater than 4 for the long range case, which means we need to put the laser at 100% and disable any of the flood settings. And we need to go back to the start. Add a label there right quick. So this way we know we have any of the higher end cases taken care of. We'll have to wait and see if we need to worry about any kind of case that's longer than the specified units or not. Right now, let's assume we don't until proven otherwise. I would assume in those cases we just wouldn't get a pulse back, but it's unspecified in the documentation, so we'll have to just try it. And now we need to check for the mid-range, if we're greater than 2, because we already know we're not greater than 4 if we're here. And if we are, we need to set mid-range settings, which is set the laser to 50, and then set our flood to 20 degrees, which is the middle spot, which right here. So that's the 10. So move 10 to X2. And if we're not, we need to disable the laser because we're at the close range one and just enable the wide range flood of 60. So let's remove that. Okay, so let's give this a shot and see if it works. All right, that worked pretty well. Let's go do a couple of quick ones to see if we can get the power lower. I'm just going to fast forward it and bring y'all back afterwards. So it looks like our really cheap little Sleep 2 was the ideal number. But let's do a quick line count to see if we can actually fit either of these on a smaller chip. This one we cannot. This one is 1, 2, 3, 4, 6, 7, 8, 9, 10. So now we have a choice. Do we go for a cheaper, less lines of code solution, or do we go for the lower power usage solution? Since there were people that were really beating the tar out of us on power, let's go for the cheaper and less lines of code solution. So we take this, grab one of these, that. Unfortunately, if you try to cut and paste with something that doesn't have the right number of lines, it won't let you. And then we need to change this to X1. All right, let's see if this works. Looking good so far. So our power usage wasn't that much worse. Wow, someone's able to really reduce the production cost. You know, it'd be nice to see if there was a way to do like a Venn diagram of these so you could see that the people that were able to hit this production cost also were at this power and these lines of code. I have no idea how you would do that short of some kind of 3D chart, but it would be cool. Otherwise, I really think that most people have to optimize for one kind of thing or the other. Some of them, things will kind of come with other things. So when you can really simplify the number of lines of code, you can really cut down on certain other things. But typically at the end of the day, you have to pick one and optimize for it specifically. Let's go see what happens. Ooh, a pocket oracle. I don't think Carl is much of a fan of guns. Kind of gonna go out on a limb here. So that was good. We were able to do a fairly reasonable solution and even optimize it a little bit. Let's go look at the next one. Aquaponics robot. So we basically just need to make a control system for a robot farmer. Got it. Alright, so we have a non-blocking radio receiver. It's becoming a very common thing. We have a motor, a bidirectional motor. I think that's new. Starts at 0, 150, and 0, 50. Okay, so it'll probably be baselining at 50 again. And here's the data packet of where to go to, cleaning, and then feed time. Okay, so look at the verification. I will say I do like these little nifty graphics here in the corner. Instead of just looking at IO lines all the time, it's neat. We have 3 outputs. 2 of them look somewhat discrete, but it looks like they're going to have times with them. I'm not going to throw one of the digital I/O pins at them quite yet, since that is one of the trade-offs of using the digital I/O expander is then you can't do the gen pulse. And looking at the clean and feeds, they look like perfect gen pulse times because it's basically just a time, and you do that, and then when that ends, then you do the next one. Probably going to want to hold off on using a digital I/O expander on those. And yes, we're going to want to sit at 50 when we're not doing anything. Now that's interesting. I wonder if we can do something fancy here because down, up, down. Let's go try something real quick. Do a quick experiment. We want to initialize to 50. And now we want to try doing a quick little gen pulse thing. P1, 1, 0, and then sleep 1. Let's see what happens. It looks like we can almost use that. Wouldn't really work for this case, but it does have 2 arguments. Ooh, let's try this. See what this does. And I think we're going to have to add a reset to that so that it resets to the baseline each time. Hey. So I think we can use that. Let's try this one again real quick just to see if it does what I think it'll do. Yes. Okay. So that looks nice, and that we can probably use that as a way of controlling the motor. The question is, can we fit all this on one chip, or are we going to have to use two? If we want to use GenPulse for all of them, we're going to have to use at least two. And we also have to keep track of our current station and whether we need to move or not. Because if you look here at this last one, it was told to move to 0, and it moved there. And then it was told to move to 0 again. It did not move and immediately just started doing the tool operation. Even if we use GenPulse, I think that's going to be quite a bit of code. So let's go for the 2 chip. Actually, on second thought, let's leave you up here so you can get a straight run there. Let's go add a friend for you over here. A little too overeager there. Yeah, let's do that. Okay. Actually, let's make this a little bit cleaner, shall we? Move there. Move you up here so you just straight run there. You can there. That. And you can do that. Okay. That looks a little bit cleaner. Since half the name of the game is about aesthetics, right? What do you mean functionality is more? Plus you. Okay. First things first, we need to just do nothing until we actually get a packet. So let's just do our standard wait and then move X0 to the accumulator. Test if that's equal to -999. If it is, we just need to sleep one and then jump to wait. We have our wait loop done. Now we want to think this through. So we need to have one chip handle movement, which means it's going to need to save off the position, and depending on if it needs to move or not. But we could save a little bit of power with a few more lines of code and maybe even simplify the other one's code if it doesn't even have to worry about whether it has to move or not. So what if we only send over an instruction if it needs to move? Since the very first packet that comes in is our station destination, we save that off at the end to the DAT, and then we can just compare the accumulator and the DAT to see if we need to move. Let's do that. The DAT and the accumulator are not equal. We will move the accumulator to X3 to let the other chip know to move. And then we will sleep until we get data back on X3. We don't really need that information, but we're going to have to read the data off to get rid of it. What if we just had the other chip to give us back the position so that we can kill two birds with one stone and say, move this to the DAT? So if we have it report back the position it's at, we can clear the line and save off the value in one line. And then in the next two lines, we're going to need to do, so feed is P0 and clean comes first. So we want to do P1, X0, 0, and then gen P0, X0, 0. Okay, so now we need to go over to the other chip and figure out what we need to do. Move 50 P1 is correct. We need to set that to 50 initially. Then we're going to want to sleep on X0 until we get some data, and we're going to want to move that data to the DAT. So now we need to have our move loop, and there's a nifty command called TCP, which is, I think, test compare. It test compares A versus B, and if A is greater than B, it enables the pluses, and if B is greater than A, it enables the minuses, and then if they're equal, then it leaves both of them disabled. Sounds kind of spot on perfect for what we're looking for, doesn't it? So then what we'll want to do is say, compare the DAT with the accumulator, because the DAT is our new position. If we want to go higher, then we're going to want to add one to the accumulator, and then we're going to want to do our whole gen P1 0 thing, and then we reset it, and we sleep one. Okay, and now we also need to go back and add our going down case, track one, and then we just flip the things of what we're trying to do with the pulse. And now we just need to know when we need to stop or keep going. So we need to go check if the DAT is equal to the accumulator. If it's not, jump back to move. And as a final step, we need to go let the other chip know it needs to take back over. So we need to move the DAT to X0. Because remember, we have to go update it with our position, save on a line of code there. All right, let's see how this works. Good so far. So let's let her rip. Okay, that apparently worked better than I expected. Wow, someone got it down to what looks like 9. You get it down to a 9. Power usage isn't too surprising. Ooh, we can do a quick cheeky sleep real quick. We'll try that. Go for, looks like at best a sleep 1. But we'll try some other numbers real quick. Go for gold of 3. I didn't think it would. And a 2. Nope. So we can save a decent amount of power, but it costs us a line of code. Still puts us in a pretty decent ballpark though, so I'm not going to worry about whether it's 23 or 24. And we did save a small amount of power, which also put us about the same level. And what you gonna do? All right, let's go see what's next. Ah, yes, the fun of engineering computer science. Customer won't tell you any of the things besides the bare minimum requirements because they know best. And or they are paranoid that you're going to run off and steal their idea. I understand it. It's just a really tricky situation because oftentimes the engineers that you're asking to do stuff, if they actually know enough to understand what you're going for, really help you out in a lot of interesting and awesome ways. Let's go take a look at the other projects real quick and see what's coming up. So we know the remote quit kill switch. All the inputs are, X+ inputs are blocking, so we'll need to connect all the inputs to be read once simultaneously. That'll be interesting. Now, how about this oracle? Like we're gonna meet our friend, the random number generator. We have to generate the readings in the proper way. So why are we talking about electronics at all then? Is the proper? Yeah, well, that's one way around it. Except it still is a model and not the actual thing, so still not proper. Alright, what is the... I have nothing about that title. Apparently they have very impressive markets of scale. Interesting. Alright, and the food scale. Yeah, I think that's better. One of those questions better not to ask. You don't want to know the answer. I mean, hey, they could be avid runners. Who knows? With that, if you like, leave a like. If you didn't, leave a dislike. If you have any questions, suggestions, feedback, or advice, drop it in the box below. Good luck in your races, and y'all take it easy.